Good evening. This is for Earth Science today, April 15th. So today I have posted the sun, and we're going to go through. It's always wise to pull up the PowerPoint as we're going through the lecture so you can kind of follow along. I've also posted some student notes, so if you're able to print those out, it's a good idea to go ahead and do that and print those out and get that going. If not, then you can just write on a piece of paper as we're going along. So today is just doing the video, going over the PowerPoint, getting caught up on your CK12s and all of that. But we're going to go through. And one of the things that you want to, for the question that I'm going to post is, what you'll see on the second slide of your PowerPoint is KWL. So it's going to be, what do you know about the sun? And then what do you want to know about the sun? And so I'll go ahead and post that and put that out there and see. So going on to the third slide. So how does your sun compare to other observable stars? That's one of the things we should have read and already gone through. The sun is massive. It's huge. And then can you think of anything larger than the sun at this point? Well, maybe there's a bigger sun in another galaxy that's just as bigger. But as you kind of go through the PowerPoint, you'll see many different videos. And so I'm also going to have a second part video where I am going to be talking about the inner planets and then the outer planets. And then we are going to have an activity starting next week where you're going to go through and pick a planet and then have a list of items that you're going to do. So we're going to really dive into astronomy and what that looks like, okay? So make sure that as you're going through, if you pull it up, pull the PowerPoint up on big screen, you should be able to click on where the videos are. So let's kind of go through. The sun is 400 billion stars, is one of 400 billion stars. So the sun is a star. It's not considered a planet. You can't live on it. But there's certain cycles that your planets go through and your stars go through. And just like everything else, the star has a life. Like, it can only live and go for so long. But by the time that the sun is done and it's died out, we'll be long gone from here. The sun is Earth's primary source of energy. So we get a lot of our energy from the sun. And it is considered a main sequence star. So we're going to go into what that exactly looks like and what we're looking at. So we're going to have a two-part series with Earth Science. We're going to go into astronomy pretty deep, and then we're going to go into environmental. So anything geology-wise, there's another geology class, but here we're going to really dive into astronomy. And so the sun is actually considered what we call a yellow dwarf. Just like I said, there's steps in astronomy and what stars go through. And the pole, so when we talk about a pole, we talk about here on Earth like a North Pole, South Pole. It actually rotates every 36 days. So a little bit more than what would consider a month cycle. And what is cool about that is that when you have the North and the South spinning, right? It's spinning on its axis at 36 days. The equator, which is the center of the Earth, actually rotates every 25 days. So the center of the sun, I'm saying Earth, but the center of the sun actually rotates a little bit faster than its poles do. And what's so interesting about that is so does Earth. Earth does the exact same thing. Our poles rotate at a different pace than our actual equator does. And so that's kind of an interesting on how we're all connected or how things are connected, what we're talking about. So if you go on to slide 6, that's another video. Now, the sun's diameter, which is massive, is 109 Earth diameters. So that means 109 Earths put together, their diameter, what you would measure all the way around. If you put a times that by 109, that's how big the sun is, which is pretty massive. That means it's 1.3 million kilometers in diameter. That's massive. That's huge. when we're talking about the sun's volume, like how much can you put in there, it's 1.25 million times greater than the Earth. So that means you can put a lot in there, right? The sun is 1,000 times bigger than Jupiter. So on some of the last previous cycles we talked about, you can kind of see how you went from the inner planets, and then as you moved away from the sun, you saw how Jupiter and how many moons Jupiter had. But the sun itself is 1,000 times bigger than Jupiter. So that's still, hopefully it's coming into your head on how massive the sun actually is. It's large, but it doesn't have much density. And why is that? Because it's a gas. It's mostly gas. Remember, we talked about nuclear fusion, where hydrogen and helium come together, and as it moves from the core and moves out through the convection zone, radiative zone and convection zone, then you're talking about all that gas and reaction is actually bursting and released from the sun. So that's something that to think about that, okay? As you get to slide 8, you start to see the structure of the sun. The sun is divided into 4 parts, and this will probably be one of your questions. What are the 4 parts of the sun? And the 4 parts are, you have a solar interior, you have a chromosphere, you have a photosphere, and then you have a corona. So even though the sun has 4 parts, you still have layers within those parts. And so that's what we're looking at. Now, as you can see, the solar interior, when you get to 9, you have the internal structure. You have the core, which is the very center of the sun, and then you have the radiative zone, and then the convection zone. And so that, remember, that's all moving outwards to the surface of the sun. So we're starting from the very center and looking at. So that solar interior is what we're looking at. And then as you move out, you start to get like that photosphere and the corona. So make sure that you kind of look at that, okay? So what is the core? The core is the center of the sun. It is the most compressed part of the sun due to that gravity. Remember, we talked about how does everything stay within its ellipsis orbital, right? And that's because of the gravity of the sun keeps it in its rotation, right? Because if it didn't have that, everything would just crash into each other. Nothing would ever stay put. And so it is the hottest and densest region of the sun. And actually, this is where nuclear fusion occurs, in the core. As you start to move out, the next layer within the interior part, the interior zone, is the radiative zone. And actually, that is the middle zone. And so it is really where, as nuclear fusion happens, so your hydrogen and your helium have fused together, and it's now that energy is moving out from the core to the radiative zone. This is where the thermal radiation energy, thermal is temperature, radiation is that hot sun, right? And this is actually where photons are carried. So we see, and then the waves kind of move out with that. It makes up, now the radiative zone makes up 85% of the sun's radius. So just think about that. The convection zone now, so you have 3 zones. You have the core, the radiative zone, and the convection zone. And the convection zone actually is pretty wide, but it actually sits just beneath the surface of the sun. It's still on the interior part, but it's sitting right at below that surface. And actually, as the nuclear fusion and that energy, that thermal radiation has moved out, it's starting to boil now in that convection zone. It's a lot of heat, a lot of stuff that is moving around, and it really wants to get going. And it actually can be compared to boiling water, really. You add heat to it, and what happens? Well, those bubbles start happening, and then it's sitting and it's starting to boil now and get going. Okay, so then you have another video that you can watch on slide 11. And then on slide 13, it goes through what nuclear fusion is. Now, I'm not going to test you on what nuclear fusion is, 4 hydrogen to 1 helium. You would know that, but as far as like what the mass is, you don't have to know that. So one of the things that nuclear fusion does when you have 4 hydrogen to 1 helium, and it's taking place in that core, really, this is why stars shine, have such a bright, we can see them from millions and millions of miles away, is because of that nuclear fusion. And so as it's happening in the core, that thermal radiation, we can often see radiation come out, right? Thermal, that heat that's happening. And energy is released because matter is converted to that energy, right? So this often goes to, why can we see them? Well, that's that energy times mass towards speed of light. So things are moving very, very fast, and we're able to see that from so far away because of the speed of light. And that's how that plays a role in that. 14, slide 14 is another video where you get to see the fusion power of the sun. So make sure you watch that. All right. As we're looking in, we are going to talk about the sun's surface. So the sun's surface includes the photosphere, chromosphere, and corona. So remembering the interior has 3 layers, the core, radiative zone, and convection zone. And now the convection zone sits right below the surface. Now we've gone to the surface, and that has 3 more layers. And so that has a photosphere, a chromosphere, and a corona. And so what does that exactly look like? Well, the photosphere is the boundary between the sun's interior and solar atmosphere. So you have the convection zone, and now you've hit the photosphere. And so that radiates. That's what we see, the photo. Sometimes you think of photo, that's what we're seeing is the photosphere. And it's actually one of the thinnest layers of the sun. So 90% of the sun's surface atoms are hydrogen, and the other 10% is helium. And if you think about that in nuclear fusion, that would kind of make sense, right? You have 4 hydrogen to 1 helium. So as you go and you hit to the surface, it would make sense that the surface would have more hydrogen than it would helium, as we think about that. All right, remember to watch the videos as we go through. And the granules. Granules are kind of markings on the photosphere. They are really kind of narrow, really dark black spots that we're looking at. To us, they look tiny, but actually when you get up there, it's the size of Texas, so that's still pretty big. And this happens because as the 4 hydrogen and that nuclear fusion, that thermal radiation starts going, it's the hot and that boiling water we were talking that's happening in the convection zone. They really, after a while, they cool. Once it boils out, you have regions that cool, and then they darken, and then they sink back. So just think of it as it boils and it pops. What happens? It kind of comes back. And then really a sink back into that interior due to the convection that's happening, that boiling water. And so that lasts about 10 to 20 minutes. And so as you're looking at that, that's kind of what it's doing. It's, if you think about boiling water, and it boils and a bubble happens, and then it bursts, right? And what happens when it bursts? That water sinks right back in. So you can think of that as it's sinking back in, it's becoming dark and black. But the size of Texas is a pretty big region when that happens compared to the sun. And let me see, you will be able to see that on slide 19 if you go through. Okay? So what happens, those dark regions that are happening are called sunspots, right? Low temperature, it boils up about 1500 Kelvin less than the surrounding solar surface. So when that happens in those dark regions, it actually is a cool spot that happens. It's not really cool. It's just 1500 Kelvin cooler than the surrounding part that's still boiling and having a lot of heat. The number of observable sunspots that get to see is every 11 years there seem to be more than others. So they kind of do their own little cycle that happens. So once something happens, it lasts about 11 years, and then new ones and the old ones go away. So just think about that. All right, chromosphere lies above the photosphere. So now you have the convection zone, the photosphere, now you have the chromosphere. So now we're still on the outside, outer layers, photosphere, chromosphere. And this is the lower atmosphere of the sun. It is 10,000 times less dense than photosphere, so it's kind of like become even more gaseous, even thinner is what it's talking about. And that contains hydrogen gas, right? Which would make sense still, because if you're 4 hydrogen to 1 helium, it's still now going to be predominantly hydrogen. And this is actually what can be viewed during a total eclipse of the sun. Remember, we talked about a lunar eclipse and solar eclipse, so when things totally black out, and just looking at that. All right, prominences that happen on the chromosphere. This is gas bursts, basically. So what you're doing is, like, as it becomes less dense and more gaseous and thinned out, and mostly hydrogen, you have almost like flares that are happening at that prominent level. And then, but they're kind of still trapped within a magnetic field. So even though they burst off the surface, as you can see in the picture, that magnetic pull keeps them still within range. But when it does happen, it actually often will appear like arches coming off that, so it'll extend out like an arch into the corona. So it'll burst out of out of that chromosphere, and stay within a region, but enter the third layer, corona layer. So but if the burst is pretty, has a lot of energy behind it, it can actually leave the sun completely, and it has done that before. So when we're talking about the third outer layer, which is the corona, this is the outermost portion. It's considered the crown because it surrounds it. It is only visible when the photosphere is completely covered. And that actually is what gives it a total eclipse, a solar eclipse. It actually has a higher temperature than photosphere, but by the time that you hit the corona layer, it really doesn't have as much energy because of its low density. Right? So what happens in the corona as well is that you have what we consider solar flares. These really are like brief and intense outbursts. They burst out, release a large amount of energy, and sometimes, and usually it takes about a day for those atoms that are ejected, so such a prominent and burst out, that it takes about a day for them to actually hit Earth. And when they do, sometimes they can interfere with our communication satellites. So sometimes if we have disruptions in communication, something gets outbursted, something goes awry, from our telephones to how we use our computers, Wi-Fi. Sometimes a violent outburst out of the corona, a solar flare, can completely throw off our communication satellites on Earth. So I thought that was interesting. All right. So make sure you watch the video on solar flare. Solar flare sometimes can often lead to solar winds. And so what does that mean? Well, what happens is, even though you have these solar outbursts, you can have solar winds that pick it up. And this is all happening within the corona outer layer. That kind of energy builds up, if you think about it, speeds escape, and then they escape and pull from the sun. They interact with the solar system, so things that are going on, and it actually helps create auroras. So those beautiful lights, that we see on Earth actually are part of our solar winds. And they actually can interfere as well with long distance communication. So I think that's pretty interesting. On 28, the Aurora Borealis, which is up by the North Pole, is absolutely beautiful, but that has to do with atomic release out of the corona that help create those beautiful lights and that solar wind. So very interesting. So make sure you watch that video that is posted on there. So how do solar flares actually cause auroras? Well, it's because of the Earth's magnetic poles themselves. So we have two poles. We have the North Pole and the South Pole. And the North Pole, when the lights shine up, it's called an aurora borealis, and the South Pole is aurora australis. So you have the north and south. But what's happening is particles are released when you have these prominent flares, and they're released, and the sun interacts then with these particles that then once it hits Earth's atmosphere, it actually interacts with other atoms called oxygen and nitrogen gases. And those interactions actually cause beautiful lights within the aurora borealis. And so oxygen, all these atoms, when they interact, have certain colors. And oxygen has that beautiful green, and the nitrogen can create a blue and sometimes purplish color. So it's quite interesting. All right, make sure that you review all that and that you go through that, okay? And I hope you enjoy this. I hope you learned a lot. If you have any questions, make sure you join the Zoom or make an appointment with me so we can have a Zoom date. All right, have a good night, guys. Bye.